The animal didn't cross the street because it was too tired. Now change just one word. The animal didn't cross the street because it was too wide. Say both sentences out loud and something clicks in your head instantly. In the first sentence, it is the animal. In the second, it is the street. Nothing in the grammar changed, only one word swapped, tired for wide, and the whole meaning of the pronoun flipped along with it. Here's another version of the same trick. The trophy doesn't fit in the suitcase because it is too big. In that sentence, it is the trophy, too big to fit inside. Now swap big for small. The trophy doesn't fit in the suitcase because it is too small. Suddenly, it is the suitcase, too small to hold the trophy. One word changed and the pronoun jumped from one noun to a completely different one. Somehow, without a diagram, without a lookup table, your brain just knows which one is right. Ambiguity shows up in another way too, not just in who a pronoun points to, but in what a single word even means. I sat by the bank of the river, and I withdrew cash from the bank downtown. Use the exact same word. Same spelling, same sound, two completely different meanings. Nobody reading those two sentences ever confuses a riverbank with a building full of cash machines. The word bank borrows its meaning entirely from the words sitting right next to it. And it can get even stranger than that. Take the old line, time flies like an arrow, fruit flies like a banana. Read it once and it sounds like one neat little comparison repeated twice. Read it again and the two halves turn out to not even be the same kind of sentence. In the first half, flies is a verb and like means similar to. In the second half, fruit flies is a type of insect and like means enjoys. Same words, almost the same order, and yet completely different grammar underneath. Your brain repasses the whole thing without missing a beat. Here's the strange part. None of this feels hard to a human being. You don't pause, you don't consciously work through grammar rules. The right meaning just arrives, instantly and unconsciously. Now hand that same handful of sentences to a machine, and the shortcut disappears completely. A machine reading word by word has no built-in instinct for which noun a pronoun belongs to. It has no instinct for which meaning of bank is in play either. To get any of this right, a machine has to do something far more deliberate. It has to compare every word in the sentence against every other word and weigh how much each one matters to the others. The word it has to somehow reach back across the sentence, check itself against animal and against street, and land on whichever one actually fits. That, in one sentence, is the problem this entire video is going to answer. How does a machine figure out what a word means, given the specific words sitting around it? Get that problem right, and you can translate languages, answer questions, write working code, hold a real conversation. Get it wrong, and every one of those tasks falls apart at the very first ambiguous pronoun. There is a mechanism now sitting at the heart of modern artificial intelligence, built specifically to solve this exact problem. It's called attention, and its entire job is to let a model look at a whole sentence at once, weighing every word against every other word, instead of reading one word in isolation and hoping for the best. That's the trick that lets "it was too tired" point to the animal, and "it was too wide" point to the street, inside a machine that runs on nothing but math. And here's the part worth sitting with. That exact trick is running right now, in real time, inside GPT, inside Claude, inside Gemini, every single time you type a sentence to any of them. Every one of those systems is built, layer after layer, on the same underlying idea. Let every word attend to every other word. But attention like this did not appear out of nowhere in 2017. Researchers spent years trying to solve exactly this problem with a very different kind of machine, one that read a sentence one word at a time in strict order. So before we get to attention itself, it's worth asking what the world looked like right before it, and why reading one word at a time was never going to be enough. So what did engineers actually build before any of this attention trick had a name? For decades, the standard tool for language was a family of models called recurrent neural networks, or RNNs. An RNN reads a sentence exactly the way you might read it aloud, one word at a time, left to right. At each step, it keeps a running summary called a hidden state, updating that summary as the next word comes in. Formally, the hidden state at time t depends directly on the hidden state at time t-1. That single dependency is the whole story, and it creates a hard constraint. You cannot compute step 500 until step 499 is finished. Every word waits in line behind the word before it. On modern hardware, that's a real problem, because GPUs are built to do thousands of independent calculations at once, not one after another. Training an RNN can't spread that sequential chain across the sequence itself. The only parallelism left is across separate examples in a batch, which is a far smaller win. So even setting accuracy aside for a moment, RNNs were simply slow to train, by design. But there was a second problem, and this one was about memory, not speed. To connect a word early in a passage to a word much later, the network has to pass information through every single step in between. And at each step, that information gets multiplied by the same weight matrix, over and over again. Multiply a number by something slightly less than 1 a few hundred times, and it shrinks towards 0. Multiply by something slightly more than 1 instead, and it explodes. This is the vanishing and exploding gradient problem, and in practice, it meant a plain RNN struggled to learn any dependency stretching much beyond 10 or 20 tokens. Say something in sentence 1 that matters for sentence 10, and a vanilla RNN had probably already forgotten it by the time it got there. In 1997, Hochreiter and Schmidhuber proposed a fix called the LSTM, the Long Short-Term Memory Network. LSTMs add gates, small learned switches that decide what to keep, what to forget, and what to write into memory at every step. That gating genuinely helped. An LSTM could hold on to information for far longer than a plain RNN could. But gating didn't eliminate the underlying problem. It only pushed the breaking point further out. Very long sequences could still lose the thread. And an LSTM was still just as sequential as before. Step 500 still had to wait for step 499. Now stack a second layer of difficulty on top of this, translating an entire sentence from one language into another. In 2014, Sutskever, Vinyals, and Lair proposed an architecture called sequence-to-sequence, or seek-to-seek, built for exactly that job. One RNN, the encoder, reads the whole input sentence and compresses everything it read into a single fixed-length vector. A second RNN, the decoder, then has to generate the entire translated sentence, starting from nothing but that one vector. Think about what that means. A sentence with 3 words and a sentence with 80 words both get squeezed down into a vector of the exact same size. For short sentences, this worked reasonably well. For long sentences, it did not. Translation quality fell off sharply because that one fixed vector simply couldn't hold everything the decoder needed. It's a bottleneck in the most literal sense, an entire sentence's meaning forced through a single point. Researchers noticed the obvious question: why compress everything into one vector at all if the encoder already computed a hidden state for every single word along the way? In 2014, Bottleneck, Cho, and Benjo answered that question, and their answer was the first real attention mechanism. Instead of handing the decoder one fixed vector, their model let the decoder look back at all of the encoder's hidden states at every single output step. At each step, it computed a weighted sum across every one of those hidden states, learning which earlier words deserved more weight for the word being generated right now. That was a genuine breakthrough. Translation quality on long sentences improved immediately. In 2015, Luong, Pham, and Manning simplified the idea, showing that a simple dot product between the decoder state and an encoder state could work just as well as fancier scoring methods. But look closely at both of these systems, and the recurrence is still sitting right there underneath. Bottleneck's model and Luong's model were both still built on top of a recurrent encoder and a recurrent decoder. The attention part could finally look at an entire sentence at once, exactly the ability we need, but it was bolted onto a sequential engine that still processed one token at a time. So the slow, step-by-step training bottleneck never actually went away, even as translation quality kept improving. Attention could already look at everything, but it was still trapped inside a slow, sequential recurrent loop. What if you tore out the recurrence and kept only the attention? That question got answered within a single paper, published in 2017, with a title that reads almost like a dare. It's called Attention is All You Need. 8 researchers wrote it: Vaswani, Shazir, Parmar, Sqrt, Jones, Gomez, Kaiser, and Polasukin. Most of them at Google Brain and Google Research. It appeared at NeurIPS in 2017, and it's still findable today under the reference archive 1706.03762. Here's the map for the rest of this video, so you always know where you are. First tokens, then positions, then attention itself, then the full block those pieces get built into. But first, get clear on what this paper actually claimed, because the title is easy to misread. It is not claiming to have invented attention. Attention already existed by 2017. Bardano's version from 2014, Luong's from 2015, both stitched onto recurrent encoders and decoders. What this paper claimed was something narrower and far more radical. Rip out the recurrence completely, rip out convolution too, and build the entire model from nothing but attention and feed-forward layers. No loop, no step-by-step hidden state carried token by token. Just attention, doing the whole job by itself. Zoom out, and the resulting shape is simple. 2 stacks facing each other. An encoder stack reads the entire input sentence at once and turns it into a rich representation. A decoder stack generates the output 1 token at a time, reaching back into that representation as it writes. Every layer in both stacks is built from the same small kit of parts: self-attention, a feed-forward network, and the connective tissue holding them together. That's the skeleton every later part of this video will zoom into. Now put actual numbers on that skeleton, because the paper describes 2 versions of it. The base model stacks 6 encoder layers and 6 decoder layers. Its internal vector width, called D model, is 512. It splits attention into 8 parallel heads. Its feed-forward layers widen out to 2048. Altogether, that's a model of roughly 65 million parameters. Tiny by today's standards, but that smallness was the whole point. The big model keeps the same 6 encoder and 6 decoder layers. It widens D model to 1024, uses 16 heads instead of 8, and expands its feed-forward layers to 4096. That version lands at roughly 213 million parameters. Now the results, tested on the standard machine translation benchmark of the time, WMT 2014, English to German and English to French. On English to German, the big model scored 28.4 blur. That beat the previous best score, including systems that combined several models together, called ensembles, by more than 2 full blur points. On English to French, it scored 41.8 blur, a new record for any single model on that benchmark. Strong scores get published every year, so the numbers alone weren't what made people sit up. The real jolt was buried in the training section. This entire result came from training on just 8 NVIDIA P100 GPUs. The base model finished training in 12 hours, 100,000 steps. The big model, the one holding both translation records, finished in 3.5 days, 300,000 steps. Compare that to what recurrent models needed to reach similar quality, grinding through a sequence 1 token at a time with no way to parallelize across it. Take the recurrence away, and a GPU built for parallel matrix math can finally do the job it was actually designed for. The authors said as much directly, describing this training cost as a small fraction of what earlier state-of-the-art models had required. Better translations, produced in a fraction of the compute. That combination is what actually made the rest of the field stop and pay attention. So the title's claim held up. No recurrence anywhere, no convolution anywhere, and the results still got better, not worse. But none of that math can run yet, because right now a sentence is still just a string of letters on a page. Before a single query can be compared to a single key, that sentence first has to become something a neural network can actually compute on: numbers. Start at the very first step. Take a sentence like, "The cat sat on the mat," and ask how a neural network could possibly read it. Neural networks only understand numbers, So before anything else, that sentence has to be chopped into pieces called tokens. The obvious choice would be to just use whole words, but that runs into trouble almost immediately. A vocabulary built from whole words would need an entry for every word in the language, plus every rare name, typo, and made-up term anyone might ever type. Miss one, and the model hits an unknown word it has literally never seen, with no way to represent it at all. So what about going the opposite direction, breaking everything down into individual characters? That fixes the missing word problem completely, since any word can always be spelled out letter by letter. But now every sentence turns into a very long sequence of tiny, almost meaningless symbols, and the model has to do far more work just to reconstruct what a word even is. The compromise the field settled on is called a subword, a piece bigger than a single letter but smaller than a whole word. Common words like the or cat stay as single tokens, while rare or unfamiliar words get split into smaller, reusable chunks. The most widely used method for building this kind of vocabulary is called byte pair encoding, or BPE. BPE starts from individual characters and repeatedly merges whichever pair of adjacent symbols shows up most often in the training text. Run that merging step tens of thousands of times, and you end up with a vocabulary of subword units, built directly from the statistics of real language. WordPiece, used by BERT, follows a similar merging idea, but it picks merges that make the training data most likely under the model rather than just picking the most frequent pair. SentencePiece takes a different angle. It treats the input as a raw stream of Unicode characters, without even assuming words are separated by spaces. That makes it naturally language agnostic, which is why models like T5 and Llama rely on it. These vocabularies are not small. BERT uses about 30,522 tokens. GPT-2 and GPT-3 use around 50,257. T5 and the first two Llama models use 32,000. Llama 3 jumps to 128,256, largely to handle many languages well. And the tokenizer behind GPT-4 uses roughly 100,277 tokens. So take an unfamiliar word, say a made-up brand name, and the tokenizer simply splits it into 2 or 3 familiar subword chunks it already has in its vocabulary. Once a sentence has been cut into tokens like this, every token gets assigned an ID number, essentially its row number in a giant lookup table. That lookup table is called an embedding table, and it's just a matrix. One row for every token in the vocabulary, and each row holds some fixed number of columns. That fixed number of columns is called d-model, and it's the size of the vector every single token becomes. The original transformer paper used a d-model of 512. BERT-base uses 768, and GPT-3 at 175 billion parameters uses a d-model of 12,288. Multiply vocabulary size by d-model and you get the size of this one table alone. For a smaller model, that single embedding table can account for a surprisingly large slice of its entire parameter budget. One reason vocabulary size is not a decision made lightly. Crucially, this vector is not some simple code for the word. It's not a one-hot flag with a single 1 and a sea of zeros. It's a dense vector. Every one of those d-model numbers has a real value, and every one of them is learned during training, nudged a little with every batch of text the model sees. And here is the genuinely elegant part. Once training is done, meaning ends up encoded as direction in space. Tokens that show up in similar contexts drift towards similar vectors, simply because the model keeps getting nudged to treat them alike. Nobody hand designs these directions. The geometry emerges entirely from the statistics of the text the model was trained on. You may have heard the famous illustration from word embeddings, where king minus man plus woman lands you somewhere close to queen. It's a nice, intuitive picture of directions encoding relationships, but it's also a cherry-picked example. Most pairs of words don't line up nearly that cleanly, so treat it as a rough tendency in the space, not an exact, guaranteed algebraic law. Still, the underlying idea holds up. This space genuinely organizes itself by meaning, clustering related concepts and separating unrelated ones. So at this point, every word in our sentence has become a vector, a point floating somewhere in a very high-dimensional space. But look closely at what we actually have. Just a set, a pile of these vectors, with no notion of first, second, or last. And that's a real problem, because a pile of vectors treats dog bites man and man bites dog as containing exactly the same information. Somehow, this model has to be told which word came first, second, and third, and nothing we've built so far does that. That gap is not a small oversight. It's baked into the mathematics of attention itself, and it has a name: permutation invariance. Take the exact set of word vectors for dog bites man, shuffle their order into man bites dog, and feed both into a self-attention layer. Every pairwise comparison it makes comes out identical, just relabeled, because attention only ever looks at the vectors themselves, never at the order they arrived in. So as far as the raw mechanism is concerned, a sentence is just a bag of vectors, and a bag has no first, second, or third. Position has to be injected on purpose before attention ever runs, or the model stays permanently blind to word order. The original 2017 Transformer paper solved this with something called a positional encoding, built directly from sine and cosine waves. Here's the setup. Every even dimension of the position vector gets a sine wave. Sine of the position divided by 10,000 raised to the power of 2i over d model. And every odd dimension gets the matching cosine wave of that same expression. Cosine of the position divided by 10,000 raised to the power of 2i over d model. That vector isn't concatenated onto the word embedding. It's added directly on top of it, so meaning and position end up sharing the exact same space. What makes the formula clever is the I sitting in the exponent. It changes the frequency of the wave at every pair of dimensions. Early dimensions oscillate very fast, completing a full cycle every few tokens. Later dimensions oscillate extremely slowly, barely shifting over thousands of tokens. Picture a clock with dozens of hands instead of 3. A second hand, a minute hand, an hour hand, and several more spinning even slower than that. At any instant, the exact combination of where every hand points pins down one unique moment in time, even though each individual hand alone just keeps repeating itself. It's the same trick a binary counter uses. The last digit flips every single step, the next digit flips half as often, and so on, until a handful of digits can uniquely count into the millions. Sines and cosines do the same job, just smoothly instead of with hard flips. And that smoothness is exactly the point. Because the code changes continuously, two nearby positions end up with nearby encodings, so the model can reason about relative distance, not just recognize each position as some unrelated symbol. The paper's authors even showed that the encoding at any position, offset by some fixed distance k, can be written as a simple linear function of the encoding at the original position. In plain terms, how far apart are these two tokens is recoverable directly from the math, not just which exact slot is this. And that was the whole motivation. A fixed formula instead of a learned one, so the model might generalize to sentences longer than anything it trained on. Many later models took a simpler road instead, learned positional embeddings. Here, position 0 gets its own trainable vector, position 1 gets a different one, and so on, learned by gradient descent exactly like every other parameter. No sine waves involved. But GPT-2 and GPT-3 all did this, and in practice it works well. But it comes with an obvious ceiling. If training only ever showed the model positions up to 2048, there simply is no learned vector for position 2049. Push the model past the sequence length it trained on, and it has nothing meaningful to fall back on. That extrapolation problem is exactly what pulled the field towards something newer. ROPE, short for Rotary Position Embedding, introduced by Su and colleagues in 2021. ROPE throws out the idea of adding a position vector altogether. Instead, it rotates the query and key vectors themselves by an angle that grows with the token's position. Picture each pair of dimensions in a vector as its own tiny two-dimensional plane, like a single clock hand living inside a much bigger vector. A token at position 2 gets that hand rotated a little, A token at position 100 gets it rotated much further around. Now here's the payoff. When the model later takes the dot product between a rotated query and a rotated key, something elegant happens to the math. The absolute rotation angles cancel out almost entirely, leaving a result that depends only on the difference between the two positions, not on where either token actually sits in the sentence. In other words, relative position falls directly out of the geometry, instead of being glued on as a separate vector beforehand. Because that relative structure is built into the mechanism itself, ROPE tends to generalize more gracefully to sequences longer than training ever covered. That's exactly why it has become the de facto default in modern large language models. Llama, Palm, Mistral, GLM, and most other open frontier models all rely on it. One more approach is worth knowing. Alibi from Press & colleagues, also in 2021. Alibi doesn't touch the query, key, or value vectors at all. It simply adds a fixed, non-learned penalty straight onto the raw attention scores, one that grows with the distance between two positions. That penalty quietly biases the model toward nearby tokens by default, while still leaving long-range attention available, and it extrapolates cleanly to sequences far beyond what it saw in training. What actually pulled the field toward ROPE and its relatives wasn't translation quality on some fixed benchmark. It was exactly this extrapolation problem. Keeping models stable and coherent had context windows nobody trained them on. So every token entering the next stage now carries two things fused together: what it means and where it sits. The next question is the one the whole architecture actually exists to answer. How does one token decide, out of every other token in the sentence, which ones it should actually look at? Time to finally open the black box. Every token in a sentence is about to ask itself a question. That question is called a query. What am I actually looking for from the rest of this sentence? Every token also has an answer ready in case some other token comes looking for exactly what it offers. That answer is called a key. Here's what I contain, here's what I can be found by. And every token is carrying something real it can actually hand over once it gets picked. That's the value, the actual content it contributes when a match is made. Query, key, and value are not three different tokens sitting in three different places in the sentence. They are three different views of the exact same token. Each one starts from the very same input vector we built when we turned words into numbers. The model multiplies that one vector by three separate learned weight matrices. One that produces queries, one that produces keys, one that produces values. Same starting point, three different lenses. What am I looking for? What do I offer? And what would I actually give if chosen? None of these three matrices was designed by a person. All three are learned from data, adjusted a little every time the model gets a prediction wrong during training. So why go to the trouble of building three separate vectors instead of just comparing tokens directly? Because this setup turns attention into something like a lookup, just a far softer one than any lookup you've used before. Picture an ordinary dictionary or database. You type in an exact key, and if it matches, you get back exactly one value. No match means no result. It's a hard binary decision, yes or no. Self-attention throws that binary rule out entirely. A token's query doesn't demand one exact key match. It compares itself against every single key in the sentence at the same time. Each comparison produces a degree of match rather than a pass or fail answer. Some keys line up closely, some barely at all, most somewhere in between. Those degrees of match become weights, and a token's output ends up as a blend of every other token's value, weighted by how well each key matched. So instead of retrieving one fixed answer, every token retrieves a little bit of everything, in proportions the model itself decides. That single shift from a hard match to a graded and continuous one is exactly what makes the whole thing differentiable. And differentiable means trainable. Nudge the weight matrices slightly, the blend shifts slightly, and gradient descent can search for matrices that produce better blends. Let's make all of this concrete with the sentence this video opened on. The animal didn't cross the street because it was too tired. By the time the model reaches the word it, that token builds a query that's effectively asking which earlier noun it should be pointing back to. Every other word in the sentence, animal, street, cross, tired, has already produced its own key. The query from it gets compared against all of them, and the comparison against the key from animal comes out far stronger than the comparison against the key from street. Swap the last word to wide instead of tired, and the key for street suddenly lines up better with that same kind of query. The weights flip, and so does the meaning of it. Picture it as a small chart of weights spread across the sentence. Most of the weight piled onto animal, a sliver on tired, almost nothing on street. That blend is what the model actually uses to build its final representation of the word it. And critically, nobody handwrote a rule saying pronouns should attend back to nearby nouns. The model discovered on its own that attending this way reduces its prediction error, and training simply kept reinforcing it. One more detail worth noticing. None of this required scanning the sentence one word at a time. Every token computes its own query, key, and value and compares itself against every other token all at once in parallel. That's the exact sequential bottleneck an RNN could never escape. Gone completely. So the intuition is complete. A soft, learned lookup where every token asks, every token answers, and every token blends in a little of everything based on how well the asking and the answering line up. What's still missing is a precise number for exactly how much to blend. Right now, we only have loose language like stronger or barely at all. Next, one line of math turns that fuzzy sense of matching into an exact, calculable weight. Every token now has a query, a key, and a value. Time to turn that comparison into real arithmetic. Start with just two vectors, one query and one key. The simplest way to score how well they match is a dot product. Multiply their matching numbers together and add up the results. A large positive dot product means the two vectors point in a similar direction, a strong match. A dot product near zero means the two vectors are basically unrelated. A negative dot product means they point in opposite directions, an active mismatch. So the dot product is exactly the similarity score attention needs. Now scale this up. Stack every token's query into one matrix, Q, and every token's key into another matrix, K. Multiply Q by K transposed, and every query gets compared against every key all at once. For a sentence of n tokens, that single multiplication produces a score for every possible pair of tokens. So Q times K transposed comes out as an n by n matrix. Entry ij is how strongly token i's query matches token j's key. The whole sentence scored against itself in one shot. But those raw scores hide a problem, straight out of the math of high-dimensional vectors. Suppose each number inside a query and a key is drawn independently, with mean 0 and variance 1. Add up dk of those independent random products to get the dot product. That sum ends up with variance equal to dk itself. So the more dimensions each vector has, the bigger and more spread out these raw scores get. Purely from arithmetic, not from any real signal. Feed scores like that straight into a softmax, and the largest one drowns out everything else. Softmax turns a large enough gap into something close to a hard argmax. One weight near 1, everything else near 0. And once softmax is pinned that flat, its gradient collapses towards 0 almost everywhere. During training, that means almost no signal flows backward to correct the model. Learning stalls exactly where it matters most. The fix is almost embarrassingly simple. Divide every score by the square root of dk. Since the raw score's variance was dk, dividing by the square root of dk brings that variance back down to roughly 1. That keeps scores in a modest range, so softmax stays smooth, spreads its weight sensibly, and keeps passing gradient through training. This is exactly the reason Vaswani and his co-authors give for the scaling factor in the original paper. Not a hack, a variance correction. So here is the corrected, well-behaved score. Q times K transposed divided by the square root of dk. Now apply softmax to that matrix, one row at a time. Each row belongs to one token, and softmax turns its raw scores into a proper probability distribution. Every entry becomes non-negative, and every row adds up to exactly 1. Row I now reads as exactly how much weight token I places on every single token in the sentence, including itself. Multiply that row of weights by the matrix V, and you get the output for token I, a weighted average of every token's value vector. Do this for every row at the same time, and every token in the sentence gets a new, context-blended representation in one single pass. There's one more piece needed for a model that generates text one word at a time. A generative model can never be allowed to peek at words it hasn't produced yet. So before the softmax, every score sitting above the diagonal, every token looking at a future position, gets set to negative infinity. Why negative infinity and not just 0? Because softmax turns negative infinity into exactly 0 probability after the exponential, while a raw 0 score would still get some small, non-zero weight. Negative infinity is the only value that guarantees the future contributes absolutely nothing, which is why this trick is called causal masking. It keeps a decoder honest. Every piece is now on the table: the similarity score, the variance fix, softmax, the value blend, and the mask. Put them all together and the entire mechanism collapses into one line. Attention of Q, K, and V equals softmax of Q, K transposed divided by the square root of dk times V. That single line is the whole thing a transformer uses to let one token look at every other token. And look at what it actually is under the hood. 2 matrix multiplications with a softmax sandwiched in between. No loops, no step-by-step hidden state, nothing waiting on the previous token to finish. That's exactly why a GPU eats this alive, and exactly the thing a recurrent network could never do. But this whole computation only gives you one view of how the tokens in a sentence relate to each other. What if the model needs to track several different kinds of relationships at the same time? So what exactly can one attention head not do? Remember that formula from a moment ago. A single softmax produces a single blended pattern of focus for every token. But look at how a real sentence actually works. And a word usually needs several different relationships resolved at once. Take it from our very first example, back at the start of this video. To resolve that pronoun, the model needs to find the right noun it's pointing back to. But in the same breath, that same word also has to agree with the sentence's tense, connect to whatever was said earlier, and fit the overall topic being discussed. One softmax, one averaged blend, cannot hold all of those jobs cleanly at once. Averaging them together just blurs each one. So instead of forcing everything through one giant computation, the authors of the original paper split the problem up. Rather than running attention once over the full model dimension, they run it several times in parallel on smaller slices of that dimension. Each of these parallel copies is called a head. In the base transformer, the full dimension D model is 512. Split across 8 heads, each individual head only has to work in a subspace of 64 dimensions. Each head gets its own small query, key, and value projections, and computes attention entirely on its own inside its own slice. Once every head is done, their outputs get concatenated back together, side by side. 8 chunks of 64 dimensions concatenated add right back up to 512. That combined result then passes through one more learned matrix, the output projection, before moving on to the rest of the network. Written as one line, multi-head attention is just the concatenation of every head's output projected back down. Multi-head of Q, K, V equals concat of head 1 through head H times WO. And here's the detail that tends to surprise people. Multi-head attention does not cost more than a single head working over that same total dimension. 8 heads of 64 dimensions each add up to exactly the same 512 a single head would have used anyway. Splitting the space doesn't enlarge it, it just partitions the same budget into several independent views. So running 8 heads instead of 1 is, computationally, almost free. Think of it as a panel of specialists all reading the same sentence at the same time. One reader only checks who did what to whom. Another only checks which pronoun points back to which noun. A third tracks tense, a fourth tracks topic. And afterward, all of their notes get pooled into a single answer. This isn't just a nice story. Researchers have actually gone looking inside trained models to see what each head really does. In 2019, Clark and colleagues examined birds' heads directly and found that many of them specialize in exactly the way you'd hope. Some heads consistently attend from a verb to its direct object, others from a noun to its determiner, and others track coreference, linking a pronoun straight back to the noun it refers to. In 2022, researchers at Anthropic found something even more specific, which they called induction heads. An induction head learns a simple pattern completion rule. If token A was followed by token B earlier in the text, and A shows up again, predict B again. And these heads don't appear gradually. The Anthropic team found induction heads tend to emerge abruptly during training, showing up as a visible bump in the loss curve at almost exactly the point where a model's ability to learn from its own context sharply improves. Now, it's worth being honest about how clean the story really is. A head that cleanly tracks direct objects, or an induction head that cleanly completes a pattern, is often the best example researchers found after searching hard, not the typical head you'd see if you opened one at random. Most heads in a trained model look messier than that, doing some blend of jobs that doesn't reduce to one tidy label. In fact, a surprising number of heads turn out to be redundant and can be pruned out of a trained network with little or no drop in performance. Still, the overall picture holds. Running several heads in parallel lets one layer track several different relationships at once, instead of forcing everything through a single blurred average. Attention across all of its heads now decides where every token should look. But deciding where to look is only one job inside a much larger machine, and the next part opens the rest of it up. Zoom out for a second, past the query, the key, the value, even past the multiple heads. Attention is only one component living inside something bigger, the transformer block. Every block wraps that attention layer in a few other pieces, and each one exists to solve a very specific engineering problem. The first piece is the residual connection, an idea borrowed straight from ResNet, he and his co-authors' 2016 image recognition work. Instead of a layer replacing its input, it just adds an update on top of it. Written simply, the output is X plus sublayer of X. Think of it as a conveyor belt running the entire length of the network, a shared residual stream. Each block reaches in, edits a little information, and puts the result back on the belt, rather than rebuilding the whole representation from scratch. That design choice matters enormously because it gives gradients a direct highway back to every earlier layer during training. Without it, stacking dozens or even more than 100 layers would make gradients vanish long before they reach the earliest blocks. With it, depth becomes something you can just keep adding, which is exactly what modern large models do. The second piece is LayerNorm, introduced by Barr, Quiros, and Hinton in 2016. It normalizes each token's activations across the feature dimension, pulling them toward roughly zero mean and unit variance, then applies a learn, scale, and shift. That's different from BatchNorm, which normalizes across the batch instead of across features, a choice that doesn't work nearly as well for sequences of varying length. Per token, per feature normalization keeps activations from drifting or exploding as they pass through many stacked blocks, which stabilizes training. But where you place LayerNorm relative to the residual connection turns out to matter a lot too. The original 2017 paper used what's now called post-LN. That means normalizing after adding the residual. LayerNorm of X plus sublayer of X. That placement produces large gradients early in training, and in practice needs careful learning rate warm-up just to keep the whole thing from diverging. Pre-LN flips the order. Normalize the input to the sublayer first, then add the residual. That's X plus sublayer of LayerNorm of X. Pre-LN gives much steadier gradients regardless of depth, and is what essentially every modern large model uses, from GPT-2 onward through Llama and Palm. Post-LN is now considered the legacy choice, mostly kept around for historical accuracy when people describe the original paper. The third piece inside every block is the feed-forward network, sometimes just called the MLP. Unlike attention, which moves information between tokens, this one is applied to each token completely independently. Concretely, it multiplies the input by one weight matrix, applies an activation function, and then multiplies the result by a second weight matrix to project it back down. Along the way, it expands the model's dimension by a factor of 4, then projects it back down to where it started. In the base model, that's 512 dimensions up to 2048 and back down to 512. Here's a number that surprises most people. This feed-forward block, not attention, holds roughly 2/3 of a transformer's total parameters. Everyone assumes attention is where the smarts live, since it's the mechanism that gets all the diagrams and the famous title. But by sheer parameter count, the MLP dominates. So what is all that capacity actually doing? One influential interpretation from Giva and colleagues in 2021 treats the feed-forward network as a key-value memory. In this reading, the first weight matrix acts like a bank of keys that pattern match the input, and the second matrix supplies values that get added back into the residual stream. The rough division of labor in this view is that attention moves information between tokens, while the feed-forward network does the thinking for each token on its own and stores learned facts and patterns. It's worth being clear that this is an interpretation, a well-supported research hypothesis, not a settled, proven fact about what every transformer is doing internally. As for the activation function tucked inside that feed-forward layer, the original paper used a simple ReLU. Later models like BERT and GPT-2 and GPT-3 switched to GeLU, a smoother alternative, and more recent models like Palm and the Llama family use a gated variant called SwigLU. Now put residual connections, LayerNorm, and the feed-forward network together with the attention layer from the last part, and you have one complete transformer block. A real model isn't just one of these, it's a stack of n identical blocks, one feeding directly into the next. The original 2017 paper stacked 6 of them for the encoder and 6 for the decoder. Modern large language models stack dozens, sometimes well over 100. And here's the elegant part. Every single block has exactly the same shape, the same attention plus feed-forward structure, just with its own learned weights. That uniformity is precisely why this architecture scales so cleanly. Want a bigger model? Just add more identical blocks, no redesign required. Stack enough of them and you have a full transformer, a machine that can take in a sentence and build an extraordinarily rich representation of it. But representing a sentence and generating one are two different problems. So how does this whole stack actually produce text, one word at a time? So we've built the machine, residual stream, attention, feed-forward memory, stacked dozens of layers deep. But we still haven't said what any of it is actually for. Here's the answer. Everything up to this point exists to make one prediction over and over again. The training goal is almost embarrassingly simple. Given every word so far, predict the next one. The loss being minimized has a name, ordinary cross entropy, the same loss used in classification. It's the negative log probability of the real next token, summed across the whole sequence. And causal masking pays off here in a way that goes beyond just no peeking. Because every position is blocked from seeing the future, every single position becomes its own training example. Position 10 predicts token 11. Position 500 predicts token 501, all computed in the same forward pass, all at once in parallel. A sequence of 2,000 tokens isn't one training example, it's 2,000 of them for free in a single pass. That parallelism is a big part of why transformers train so much faster than the one token at a time RNNs this story started with. So how does an actual prediction come out the other end? After the last block, every position holds one final vector. That vector is multiplied by one more weight matrix, projecting it from the model's internal dimension out to the size of the entire vocabulary. The result is one number per possible token, called a logit. How strongly the model favors that token as the next one. Run those logits through softmax, and they become an actual probability distribution over every token the model knows. From that distribution, something has to pick the next word. The simplest option is greedy decoding. Always take the single highest probability token, deterministic but flat and repetitive. Temperature reshapes the distribution before sampling. Low temperature sharpens it toward the top choice. High temperature flattens it out, giving weaker candidates a real chance. Top P, or nucleus sampling, keeps only the smallest set of top tokens whose probabilities add up past some threshold, and samples from just that set. None of this changes the architecture, it's just a decision rule sitting on top of the same distribution. Whatever gets sampled, append it to the sequence and feed the whole thing back into the model. Predict, sample, append, repeat, one token at a time, which is exactly why it's called autoregressive generation. But look closely at that loop and something wasteful jumps out. To predict token 501, the naive approach reruns the entire sequence from token 1, recomputing key and value vectors for tokens that were already fully processed in the previous step. Those vectors haven't changed since last time. Recomputing them again is pure waste. That's exactly the problem the KV cache solves. Once a token's key and value vectors are computed, at every layer and every attention head, the model simply stores them. Generating the next token then costs one new step, not a full replay of everything that came before. But storing all of that isn't free. It costs memory, and the bill grows fast. Take a 70 billion parameter class model, around 80 layers, 64 heads, each head 128 dimensions wide. Push the context to 100,000 tokens and store everything in 16-bit precision. Work through the arithmetic, and the KV cache for that one sequence alone comes out to roughly 260 gigabytes. That's why a long conversation quietly gets more expensive to serve the further it runs. The cache keeps growing with every token generated. This also splits generation into two very different phases. Processing your prompt the first time, called prefill, looks like training. Every position computed at once, compute-bound and fully parallel. Generating the reply, called decode, is the opposite. One token at a time, limited less by raw compute than by how fast the hardware can move that growing cache in and out of memory. That's the honest reason generation can feel slower than reading a prompt. Decode is sequential and memory bandwidth bound in a way prefill simply isn't. Zoom out, and this same training objective is also what splits transformers into three architecture families. Encoder-only models like BERT see the whole input at once in both directions, built for understanding text, not writing it. Decoder-only models like GPT see only the past and train purely to predict what comes next, built for generation. Encoder-decoder models, the original architecture and later T5, keep both halves. An encoder that reads the input, a decoder that writes the output while cross-attending back to it. Decoder-only quietly won for general-purpose language models. One stack, one training rule, and unlimited raw text to learn from without needing paired input-output examples. It has one more advantage. The exact task used in training, predict the next token, is the exact task used at inference. No mismatch to bridge between the two. Of course, a raw next token predictor fresh out of pre-training is not yet an assistant. It first goes through supervised fine-tuning, or SFT, on instruction examples, then alignment through reinforcement learning from human feedback, RLHF, or the newer and simpler direct preference optimization, DPO, and only then does it start behaving like a helpful chatbot. So that's the full loop. Predict, sample, cache, repeat. And already, one long sequence can demand hundreds of gigabytes of memory just to keep the conversation going. What happens when you stop running one conversation and try to make the whole model and the context it reads truly enormous? Let's actually answer that question. Make everything bigger. And the first cost that explodes is attention itself, faster than anything else in the model. Full self-attention has a specific unforgiving cost behind it. It runs on the order of n squared times d per layer, where n is the number of tokens and d is the model's dimension. An RNN works differently. Its cost runs on the order of n times d squared, which is linear in sequence length. Attention's quadratic term is genuinely brutal in practice. Double the length of your context, and the work doesn't double, it quadruples. At 1,000 tokens, the attention score matrix already holds about 1 million entries per head per layer. Stretch the context to 100,000 tokens, and that number jumps to roughly 10 billion entries. A 10,000-fold increase for a mere 100-fold longer input. Push all the way to 1 million tokens, and a single one of these matrices holds on the order of 1 trillion entries. So why would any field willingly sign up for a cost curve that explodes like that? Because the trade-off cuts the other way too. Every token's query, key, and value can be computed at exactly the same moment, with no step waiting on the one before it. Those computations are just matrix multiplications, precisely the operation GPUs were built to chew through at massive scale. An RNN's linear cost looks cheaper on the page, but that same one token at a time wait from part 2 means it still can't put 10,000 GPU cores to work at once. Parallel hardware kept getting cheaper and more powerful through the 2010s, and a quadratic algorithm that parallelizes perfectly wins over a linear one that can't every time there's enough silicon to throw at it. Once training became cheap and parallel enough, the obvious next question was, if bigger is better, exactly how much better, and where should the extra compute actually go? Kaplan and his colleagues at OpenAI tackled that question in 2020 in a paper simply titled Scaling Laws for Neural Language Models. They found that loss falls in a smooth, predictable power law as you scale up parameters, data, or compute, almost like a physical law, not a quirky engineering result. Their headline recommendation: given a fixed compute budget, grow the model faster than you grow the training data. That recommendation shaped an entire era. GPT-3 landed at 175 billion parameters, trained on roughly 300 billion tokens, well under 2 tokens for every parameter. 2 years later, a DeepMind team led by Hoffman took a harder look at that same trade-off in the paper that introduced Chinchilla. Their conclusion was a real correction, not a footnote. Compute-optimal training needs roughly 20 tokens for every parameter, far more data relative to size than the field had been using. They proved it with a direct head-to-head comparison. Chinchilla, a 70 billion parameter model trained on 1.4 trillion tokens, outperformed Gopher, a much larger model with 280 billion parameters trained on only about 300 billion tokens, at a similar total compute budget. In other words, Gopher wasn't undersized, it was underfed. And by that same logic, a lot of that era's flagship models were too. With that lesson in hand, look at how sheer scale actually moved across less than a decade. In 2017, the original transformer ran at roughly 65 million parameters. BERT followed the next year, then GPT-2 pushed the decoder-only line forward. By 2020, GPT-3 crossed into 175 billion parameters, reading a context window of 2,048 tokens. Google's Palm reached 540 billion parameters in 2022. Meta's Llama family then proved frontier-scale models didn't have to stay locked inside one company, spanning 7 billion up to 70 billion parameters. By Llama 3 in 2024, that had grown to as much as 405 billion parameters, with context windows stretching out to 128,000 tokens. Context windows climbed on their own separate track too, moving from a couple of thousand tokens back in the GPT-3 era toward hundreds of thousands, and by some vendor claims past 1 million within just a few years. Now, here's the honest gap in that story. Today's frontier models, the very latest versions of GPT, Claude, Gemini, and their peers, simply don't have officially published parameter counts. Any specific figure you've seen floating around for those systems traces back to an unconfirmed leak, not a disclosed fact, and we won't repeat one here as if it were. So strip away every headline number, and here's what's actually changed since 2017. Almost nothing about the core mechanism itself. It's still the same block: attention, a feed-forward layer, a residual connection, normalization. What's scaled is everything around that block. More layers stacked on top of each other, more parameters inside each layer, more training tokens, more GPUs running in parallel. That is, genuinely, the entire lesson here. None of this leap in capability came from a new core idea. It's the same 2017 architecture, simply run more times, on more data, with more compute. Bigger models and longer context windows sound great until you remember the quadratic wall we just walked through. So how does the field actually make all of that affordable enough to serve to millions of people at once? So how does anyone actually afford to run a model whose core operation grows as the square of the sequence length? The answer isn't one clever fix, it's a stack of separate engineering wins, all layered on top of the exact same 2017 attention formula. Start with the one that sounds almost too simple to matter, FlashAttention, introduced by TreeDAO and collaborators in 2022. Their real insight wasn't about the math at all, it was about where the numbers had to live while the math happened. Every time a GPU computed that full n by n matrix of attention scores, it had to write the whole thing out to a large, slow pool of memory called HBM, then read it all back in for the next step. That round trip, not the multiplication itself, was the actual bottleneck. Attention was memory-bound, not compute-bound. FlashAttention's fix is to never write out the full matrix at all. It tiles the computation into small blocks that fit inside the GPU's fast on-chip memory, called SRAM, and builds up the softmax incrementally, block by block, as it goes. The output is exactly identical to standard attention, down to the last decimal. This is an exact algorithm, not an approximation. It just skips almost all of that slow memory traffic, which is why FlashAttention and its successors deliver multi-times speedups in practice, while cutting memory use from quadratic down to linear in sequence length. That single trick made long context training and inference dramatically more practical without changing one equation from the original paper. But FlashAttention only speeds up a computation that still has to happen. It doesn't shrink what has to be stored between tokens during generation. That's a separate problem, the KV cache, the very thing that ballooned toward hundreds of gigabytes in the last part. The fix there came from a different angle entirely, multi-query attention, or MQA, proposed by Noam Shazir back in 2019. The idea is almost blunt in its simplicity. Keep every query head, but let all of them share just one shared key head and one shared value head. Instead of caching a separate set of keys and values for every head, you cache just one set, shrinking the KV cache by a factor equal to roughly the number of heads, about 32 times smaller for a 32-head model. That's a direct hit on the memory bandwidth bottleneck of decoding. Less cache means less data to move for every single token you generate. The trade-off is that squeezing every head down to one shared key and value can cost some model quality. Grouped Query Attention, or GQA, introduced by Ainsley and colleagues in 2023, splits the difference. Instead of one shared pair for the whole model, query heads are split into several groups, and each group shares its own key and value head. This recovers most of the memory savings of multi-query attention, while staying much closer to full multi-head quality, which is why it's the version actually used in Llama 2's 70B model, in Llama 3, and in Mistral. So FlashAttention fixes how the computation moves through memory, and MQA and GQA fix how much even needs to be cached in the first place. A third family of tricks attacks the problem from yet another angle. Just don't let every token look at every other token. Sliding window attention, used in Mistral 7B, restricts each token to a fixed local window, 4,096 tokens back instead of the entire sequence. Stack enough layers on top of each other though, and information still effectively propagates across much longer ranges. The same way stacking convolutions extends how far a signal travels through a CNN. This sits inside a broader family of sparse and linear attention approximations that trade away a bit of raw modeling power for real savings in compute and memory. That trade-off is genuine, which is one reason these approaches tend to show up in hybrids, mixed in alongside full attention layers, rather than replacing it outright across an entire model. The last major lever doesn't touch attention at all. It targets the feed-forward layer sitting right next to it in every block. Mixture of experts replaces that single dense feed-forward network with many parallel expert networks plus a small learned router. For any given token, the router activates only a couple of those experts, not all of them. That one change decouples a model's total parameter count from how much compute it actually spends on each token. Mixtral 8x7b is a clean, openly published example. About 47B parameters in total, but only around 13B of them active for any single token passing through. The model holds far more learned capacity in its weights than it ever computes at once. And Switch Transformer pushed the same idea to 1.6 trillion total parameters. Put these together, FlashAttention's exact rewrite of the I/O pattern, MQA and GQA's shrunken cache, sparse and local attention's restricted windows, and mixture of experts' selective compute, and a pattern emerges. None of them touch the actual query key value formula from 2017. Every one of them is an engineering win stacked on top of an unchanged core. That's the honest answer to how a modern model holds an enormous context window and still gets served affordably. Not one breakthrough, but this whole stack of tricks layered on top of each other. All of this efficiency work, though, was built with one target in mind: text. And the same core mechanism was about to prove it never actually needed language in the first place. Notice something about every diagram so far in this video. It was always a sentence. But look closely at what the transformer actually requires, and language was never really the point. It doesn't need words. It needs a set of things, plus a way to measure how related any two of those things are. Cut anything into pieces small enough to call a token, and the exact same machine will attend across them. Start with a photograph. In 2020, a team led by Alexei Dosovitsky sliced an image the same way you'd cut a sheet of stamps, into a grid of small squares, 16 pixels by 16 pixels. Each patch gets flattened into a vector, exactly the way a word becomes an embedding, and a position gets stitched onto it so the model knows top left from bottom right. No convolution, no sliding filter scanning across the picture, just the same encoder from earlier in this video, now reading patches instead of words. They titled the paper, "An image is worth 16 by 16 words," and that title is not a metaphor, it's literally the architecture. Point a microphone at a room instead of a camera. Feed the sound into a spectrogram, frequency rolling forward over time, like a photograph of a sound wave, and slice that image into a sequence of frames. That's Whisper, OpenAI's speech system, trained on 680,000 hours of multilingual audio pulled from across the internet. To the transformer underneath, a frame of a spectrogram is just another token. It never needed to know it was listening instead of reading. Now go smaller than sound, smaller than pixels, down to a protein folding under a microscope. A protein is a chain of amino acids, and DeepMind's AlphaFold 2 treats that chain like a sentence, running attention over every pair of amino acids at once, not just their neighbors. That component, called the evoformer, is a major reason AlphaFold could predict a protein's three-dimensional shape well enough to reshape structural biology. Now flip the direction entirely. Instead of reading something real, generate something that starts as pure static. Image and video generators used to clean up that noise with a convolutional network called a U-net, one pixel neighborhood at a time. Diffusion transformers, introduced in 2022, tear the U-net out and replace it with patches and attention. The same recipe as the vision transformer, just predicting how to remove noise instead of predicting a label. That swap is the backbone behind the current generation of large-scale image and video generation systems. Here is where it gets interesting. Once a photograph, a sound clip, and a sentence can all become the same kind of thing, a sequence of tokens. Nothing stops you from putting them in the same stream. Clip paired an image encoder with a text encoder and trained them so a photograph of a dog and the word dog land close together in the same mathematical space. Modern multimodal systems push that further, turning image patches, audio frames, and words into one shared sequence. A token of pixel can attend directly to a token of text inside the very same layer. Try building that with a convolutional vision network bolted onto a separate recurrent language model, and you can see why it never worked nearly this cleanly before. Attention gave every kind of data the same native format. Step back, and the pattern is almost eerie. One block design, attention, a feed-forward layer, a residual connection, has become the default substrate for reading text, seeing images, hearing speech, folding proteins, and painting from noise. That convergence is remarkable, an entire field arriving, largely by accident, at one shape. It's also slightly uncomfortable. Because a monoculture has costs. When nearly everything shares one architecture, a blind spot in the transformer stops being language's problem alone. It becomes biology's, vision's, and audio's problem too. So what exactly are those blind spots? And is anything actually positioned to replace this design? For everything it can now do, ask a transformer to hold a genuinely long memory, and the strain still shows. Start with the oldest limit in the book. Attention's cost still grows with the square of how much text you feed it, and that has never truly gone away. FlashAttention and sliding windows, the tricks from a few parts back, shrink the constant factor and the memory footprint enormously. But they don't erase the underlying curve itself. Double the context and the raw computation for attention roughly quadruples. There's a second limit, quieter but just as real. Nothing you say to one of these models is remembered tomorrow. Close the chat window and the weights don't change. The conversation you just had leaves no trace inside the model itself. Everything it seems to know about you in that conversation lives only in the context window, and the moment that window closes, it's gone. Then there's the limit that gets the most attention in the press, hallucination. A model trained to predict the next plausible token was never, strictly speaking, trained to verify the truth. Fluent and confident are not the same thing as correct, and a system optimized for the first can produce the second only by accident. Bigger, better aligned models hallucinate less often on many benchmarks, but the problem doesn't vanish with scale. It just gets rarer and harder to catch. Underneath all of that sits a stranger problem. We still don't fully know what these networks have learned. Researchers can point to induction heads, to syntax-sensitive heads, to feed-forward layers that behave like memory. Real, hard-won findings. But a single neuron inside a large model often encodes several unrelated ideas at once, tangled together instead of standing for one clean concept. That tangling has a name, superposition, and untangling it is an active field called interpretability, not a solved problem with a textbook answer yet. So the architecture has real, acknowledged cracks, which raises the obvious next question. Is something else waiting to replace it? The most serious challenger goes by the name Mamba, built on an idea called the state space model. Instead of comparing every token to every other token, a state space model carries a compressed running summary forward, updating it one step at a time. That gives it something attention has never had: cost that grows only in a straight line with sequence length, not with the square of it. On paper, that's the dream. All the appetite for long context, none of the quadratic bill. And the honest verdict, as of now, is more measured than either the hype or the dismissal. Mamba has not displaced the transformer at the frontier. Nearly every leading model you can name today, GPT, Claude, Gemini, Llama, is still built on attention, not around it. What's actually happening is quieter than a changing of the guard. Researchers are exploring hybrids, weaving state space layers in alongside attention rather than tearing attention out entirely. Which points to the real shift happening right now, and it isn't inside the block at all. The core computation, query, key, value, softmax, looks almost exactly like it did in 2017. What's changed is everything wrapped around it. Context windows, stretched from a couple thousand tokens to hundreds of thousands and beyond. Retrieval systems, what the field calls RAG, now hand a model relevant documents on demand, so it doesn't have to memorize the entire internet inside its weights. Tool use lets it call a calculator, run code, search the web, and check its own answer instead of guessing from memory alone. And inference time reasoning, letting a model think in longer, more deliberate steps before it answers, squeezes more capability out of the exact same underlying block. None of that changes the mechanism itself. It changes how much the field can get out of it. Go back to the very first sentence this video opened with. The animal didn't cross the street because it was too tired, versus because it was too wide. You now know exactly what happens inside a machine to answer that question correctly. The token it builds a query and compares that query against the keys of every other word in the sentence. Tired pulls the weight toward animal, wide pulls it towards street, and a softmax turns those comparisons into one precise set of weights. Those weights blend the values of every word into a single output, and that blend is the model's answer for what it means. Multiply that single lookup by 8 heads, by anywhere from 6 to well over 100 stacked blocks, by however many billions of parameters a model carries, and by every token in every sentence anyone has ever typed into one of these systems. This same idea started as a 65 million parameter research model in 2017, built to translate sentences for a research paper. Less than a decade later, it runs inside trillion parameter systems, reading and writing across context windows 1 million tokens long. That is the whole loop closed. One small idea for resolving a pronoun, repeated at a scale that now runs underneath billions of conversations a day. And underneath every headline about artificial intelligence, underneath 1 trillion parameters, sits nothing more exotic than this. Let every element look at every other element and decide together what matters.